Hello and welcome to this video. In this video we're going to look at the equations for the capacitor behavior and more specifically looking at this idea of the time constant. So the time constant is something that pops up in the equations that we've looked at, but we haven't actually said why do we do that. So if you remember from charging and discharging, if I take a capacitor and I charge it up, the charge is going to vary as Q0 1 minus e to the minus t over RC. And if I discharge the capacitor, discharging, the charge changes as Q0 e to the minus t over RC. So these two equations are both on your formula sheet. We said these will also work for potential difference as well, but current will only have a decay. And we said that these e to the minus t over RC is just explaining an exponential decay. Okay, so in both cases, this is the same thing. This is an exponential decay. Now, this requires a small bit of maths knowledge from A-level maths. So if any of you haven't done the A-level maths spec, then this is the kind of point where they will start to separate from the people who are familiar with exponentials. So I'm going to go through a very brief introduction to exponentials and how they actually work, and we're going to use those to now explain how we can actually use these equations to calculate things like the time for each charge and so on. So first we need to take a little side note and think about when we have power. So let me half the page here, and let's say I actually want to first of all pose just a regular maths question before we come back to these exponentials. Let's say I have 2 to the power of something gives me 8. Okay, now a question might be, what power is this? Okay, what value of x can we do to actually get to 8? Now we know, because this is a fairly straightforward example, that this is just 2 cubed. So this leads to us having x is equal to 3. Okay, but what happens when you get a more complicated example? What happens if I wanted to find out 2 to the what gives me 2,562 0.45? How do I work that out? It's clearly not going to be a positive number or a whole number, because I've got some decimal here. No multiple of 2 is going to give me a decimal. And so now we come across this kind of, how do we get around this? And what we do is we introduce logarithms. So logarithms are the inverse function to the powers. Okay, so just as you could multiply and divide, you can add and subtract. Logarithms are the opposite of putting something in a power. So logarithms allow us to take something out of the power. So in general, I could write this as a to the power of x must be equal to b. Now, if I wanted to find x, I would then write in a calculator log, and you'll usually get a symbol on a calculator that has log with a little square and a big square, and the little square is known as the base, and the base is just what number is this. So this is a, and then this value here is your value. Okay, and this is b. So this means that log a of b is actually equal to x, and this is how logarithms work. Okay, so without going into the in-depth of proving why this works and stuff like that, I will leave it to you to show that actually you can prove it. If you put log of 2, 8, it will give you the answer of 3 in a calculator. Okay, and I will leave you to then show for yourself what x is here, just by saying that log of 2 of 2,562.45. Now this works for any base, but actually we have in maths some special numbers, and one of them would be pi. So pi is an irrational number that shows the relationship between the circumference of a circle and its diameter. But another one of those is e, and that's this e here. So e is the exponential factor, and actually I'm going to continue this over here. So e is a value that's around 2.71. It is also irrational, so this will go on forever as well. But it's has some very interesting properties, which means that for the most part we use this as a function itself. So as we put something into the power, we usually put it as an exponential to the power because it has some interesting properties. Now this e is just this value here, and you can find e on a calculator. It's usually there, but it means what if I have e to the power of x is equal to b, right? What happens when I have log of e? Well, this is going to end up being able to write it as log of e of b is equal to x. But actually, because this e is a special number, this log e is also known as the natural log. And this natural log has the form of ln. So this is just going to be ln of b, and you'll find this ln function on your calculator is equal to x, okay? So this is a general idea of what exponentials are. We've obviously heard the term exponential before. It means that it's just going to continue going on forever. It will exponentially increase, so you'll keep increasing until you get to infinity. Exponential decay keeps decreasing for infinite amount of time until it reaches zero. And so we're going to use some ideas here to actually be able to understand what's going on with these equations and be able to rearrange them. A fundamental thing that is introduced now is the fact that if I put a value into a function, so any value inside a function has to be unitless, or some would say dimensionless. Has to be, I'm going to go with unitless. It would be the same as dimensionless, which means in this case, if I'm going to put the power of t over rc, it means that actually t must have the same units as rc. Therefore, rc must have units of seconds. Okay, so rc, if we actually think about it, when we had the diagram before, we said that r was the resistance and c is the capacitance. Okay, so somehow if we take resistance, which is measured in ohms, and we multiply it by capacitance, which is measured in farads, we actually end up with a time. So let's prove that that is true, rather than just leaving it out for you to guess why it's true. If we were to break down the units of resistance, we know that R is equal to V over I, for example. So we could say that ohms is actually the same as volts per amp, okay? And we could say that actually the amps is a measure of current, and we could say current is measured in charge over time, which means that amps, so we'll put sections here, amps is actually the same as coulombs per second, right? And this means that if we then bring these together, we do volts, and then we substitute in coulombs per second to the -1, we end up with RC has units of volts seconds per coulomb, or even just R, for example. So R is a measure of volts seconds per coulomb, and this ends up then, if I have C, the capacitance is measured as Q over V, which is just coulombs per volt. So therefore, if I multiply that by this, I have volts per seconds per coulomb multiplied by coulombs per volt. The volts will cancel because this is -1 and 1, and the coulombs will cancel because this is -1 and 1. So I end up with the units of RC are in fact just seconds, which means this is a value of time. And we can then use this as what we call the time constant, because this value of time is a specific characteristic of the system that we have, dependent on the total capacitance and the total resistance. So this is specific to each circuit. And then we have to say, okay, but why is that specific? Why is that important? And in order to do that, we have to say, well, what happens in each of these cases for charging and discharging when I have the time that's passed is exactly the time constant. So let's scroll down here and say what happens when the t is equal to RC. Okay, so let's first take the argument of discharging. So discharging, we have the equation that Q is equal to Q naught e to the minus t over RC. And so actually if I end up with t equals RC, then I end up with a factor of e to the minus 1. Okay, because t over RC, if t is equal to RC, becomes RC over RC. Anything divided by itself is 1. And e to the minus 1, you can prove to yourself, is equal to roughly 0.37. And now what this means is after one time constant, the charge on the capacitor falls to 37% of its maximum value, or its original value. Okay, so this means that actually every time a time constant passes, we fall to 37% of the new value. Okay, this is why it's exponential, because every time we're going to consistently take 37% of the new value. It's not like it decreases by 37% each time. It decreases to 37% of what it was at the last time constant. Okay, and this is why it's an exponential decay. On the inverse of this, we can look at charging, and charging is a little bit more difficult to understand, but it means that if our charging equation is that Q is equal to Q naught 1 minus e to the minus t over RC, well, 1 minus 0.37, it leads to, so 1 minus e to the minus 1 is 1 minus 0.37, which is 0.63. So within one time constant, so after one time constant, the charge increases, in this case, increases to 63% of the maximum value. Okay, if the maximum value is Q naught, and we're saying that we're going to multiply Q naught by 0.63, we're therefore saying after the first time constant, we've increased to 63% of the original value. Now, we can't then say we're going to increase a second time to 63% of the maximum value, because that then loses its meaning, because we're already at 63%. So it's difficult from this point onwards, which is why most of the questions will only ever ask you about discharging. Now, for the last few minutes, I want to show you how to rearrange these equations. Now, I'm only going to take the example of the discharging equation. You'll find that it will be not very useful to have a look at the charging equation. But let's do an example on how I can use logs from the start of this to actually do a question on these. Now, quite a mathsy question would be, given, so let's say we have a circuit, let's actually draw out this circuit. Let's say we have an EMF source we have let's say we have this double switch again, and we have a capacitance, and this capacitance is, let's go with 10 microfarads. This is what a usual capacitance reading would be. It tends to be quite a small amount of charge. And this resistance, let's say we have a resistance of 5 ohms, for example. Okay, that means we can instantly calculate RC, since this is the resistance, which is 5, times by the capacitance, which is 10 times 10 to the minus 6, and this gives us a time constant of 5 times 10 to the minus 5 seconds. So within, this is essentially 50 microseconds, I then end up decreasing this charge when it's discharging by 37%, or to 37%. Now the question might ask, at what time will the charge on the capacitor fall to half of its original value? Okay, now this type of thing is going to come up again in another section when we look at nuclear physics in a slightly different way. But for now, we're going to have to say, if its initial value is Q0, when we switch this switch and it begins to discharge, we're initially saying that our discharging equation is Q is equal to Q0, which is our initial charge, e to the minus t over RC. Now we want to work out t. Okay, so the first thing we need to do is get the Q and Q0 onto the other side. Or actually, what would probably be an easier way of seeing it is, if Q is going to fall to be half of its original value, we could say, let's have Q0, or let's have Q being Q0 over 2, and then we can cancel out the Q naughts. Okay, so let's say that's our example for now. So we have Q over Q0 over 2, since it's half of the original value, is Q0 e to the minus t over RC. And so the Q naughts will cancel, and we end up with what we expected. This e to the minus t over RC factor is just 0.5. Now we have to try and work out, how do we actually get this t over RC out of this, and this is where we use the logarithm. Okay, so we're going to say that if I do the natural logarithm, so this is log base e of 0.5, I will end up with some value that will be equal to minus t over RC. Okay, because if you remember from before, we said if I had e to the x is equal to b, then this means that log of b is equal to x. Okay, so the same thing applies here, and this means actually then that the time it takes is going to be minus RC times the log of 0.5. Now you might be concerned that there's a negative symbol here, but actually when you calculate log of 0.5, log of 0.5 will also be negative, so the negatives will cancel. Now we know RC already, because we found out RC at the top here is minus 5 times 10 to the minus 5 times by log of 0.5, and when you put this in a calculator, you end up with 3.5 times 10 to the minus 5 seconds. So in 3.5 times 10 to the minus 5 seconds, for this specific setup with this specific resistance and this specific capacitance, or vice versa, this specific resistance and this specific capacitance, it will take 3.5 or 35 microseconds for the charge to half to exactly to its initial, to half from its initial value. Now, what I want to do before I end this video is just give you a general expression for those of you who will struggle with the maths a bit more. I want to derive an expression for t in terms of Q, Q0, and RC. So I'm going to start again at the top saying that Q must be equal to Q0 e to the minus t over RC. Now, the first thing I have to do is something similar to what I've just done. I need to make e to the minus t over RC equal to something. So I'm going to divide the Q0 across, and I end up with e to the minus t over RC is equal to Q divided by Q0. Now, this means that I'm going to have the natural log of my answer, which is Q over Q0, is actually going to be equal to minus t over RC. So this then leads to the fact that t is going to be minus RC log of Q over Q0. And this is a general expression. Now you can keep it like this. There are some logarithms that you can say. So you could say that log of Q minus log of Q0 would be the same as writing log of Q over Q0. So this is also true, and you could do this. You could also, if you wanted to, take this minus and flip these, because you could say that minus log of Q over Q0 would be the same as log of Q0 over Q, and this would also be true. But I'm going to leave it like this because I feel like this is the simplest expression that you could get for this. Okay, so you could use this for any of these questions. I would highly recommend, if you're struggling with these exponentials, go and look for some maths videos and have a look at the exponential topics and try and wrap your head around those. You obviously don't have to go into too much detail. As long as you can rearrange using exponentials and logarithms, then you're completely fine for the rest of this topic. Thank you for watching.